All right, welcome back. And today, I got an interesting topic for y'all. I hope you guys are having a great week so far. Yeah? I am. It's nice and warm and sunny outside, which is definitely my favorite time of the year. I could probably move to Hawaii right now and work there, considering we're all in quarantine. But that's okay. You know, maybe we'll be done in another couple of weeks, another month, and we'll all be back to the normal rigmarole. But let's cover today's topic for sure. So I have to admit, climate change is a very large topic, to say the least. And the problem is that it covers a lot of different fields of science. It covers astronomy, biology, oceanography, oceanology, you know, just a lot of really broad topics. And so I'm going to try to do the best job that I can, and I'm trying to be as unbiased as I can, but obviously we all have hidden biases, so forgive me if some of my bias comes through. I'm really trying to give a middle of the ground view here. Now, in the United States, this is a very highly politicized topic, and I really wish it wasn't, because it's very hard to talk to most people about climate change. One of the two major opinions that you get is either that climate change exists, but humans don't cause it, therefore there's nothing we can do and there's nothing we should care about. And those are a typical group that's called the climate deniers. And on the opposite side are people that just think the entire end of humanity is upon us and that the world's going to end in less than 10 years and we're all screwed. Now, I don't think the data supports either one of those theories, so hopefully if you're in one of those camps, I hope you continue listening, because I think you'll find today's information educational, and I think that it will shift your viewpoints at least slightly, if not at all, hopefully slightly or more than slightly, to a more middle ground position. Now, this topic is very large, so I'm probably going to break it up into a couple different episodes. And today's episode is really just focused on the science of how the climate changes, as well as how we know that humans impact the climate around us. And there's a couple different pieces to that. And then the next episode, we'll talk about how greenhouse gases affect Earth's climate, as well as some of the more extreme possibilities between a runaway greenhouse effect versus not having enough CO2 in our atmosphere. We'll discuss pros and cons across the board, whether that's pros and cons to animal life and plant vegetation on the planet, as well as how that affects our oceans. And then the final episode, what we'll get into is the effects of climate change today and what we're seeing around the globe, as well as trying to put to bed some of the myths that the data just doesn't support. So just as a quick example, is people think that there's far more wildfires than there ever will be, and that the climate, as it warms, will cause these devastating wildfires across the entire world. Well, the data doesn't support that. In fact, there's significantly less fires over time, but we'll get all of that into episode 3. So, hey, if you're new to my podcast, please subscribe. We're available both on YouTube, on Apple, iTunes, as well as Spotify and every major podcast network. The more people that I get listening, the more content that I'll be able to generate. So please give us a like, give us some feedback. If you disagree with today's topic or you have any feedback on topics that you would like in the future, I'm always open to doing more episodes. Now, let's get into this. So the first thing I want to cover today is understanding the glacial cycles. Now, the glacial cycles is a little bit of astronomy, and it all starts with a guy named Milutin Milankovitch, who in 1913, he wrote a paper that's called The Distribution of Sun's Radiation on Earth's Surface. Now, he postulates in this paper, now this is a theory written at the turn of the century, 1900s. He postulated that the gravitational effects of the larger planets would affect Earth's orbit. And this happens in 3 very important ways. So the first one is called eccentricity. And eccentricity, or elongation, is the shape of Earth's orbit over time. And that means that we slowly shift from a circular orbit into a more oval or elongated orbit over about 100,000-year cycle. Now, the other piece of that is understanding obliquity, or the tilt of the Earth. And so over a different cycle, which is 41,000 years, we shift our northern hemisphere pointing a little bit more towards the sun or a little bit less towards the sun. Now, these two things, along with the third piece of his theory, which is the precession of the Earth, really means that at some points in Earth's history, we are pointing our northern hemisphere towards the sun for longer periods of time when we're closer to the sun. So when we're closer to the sun and we're pointed towards the sun more, we have more exacerbated heat. i.e., we're in a warmer period. When we're pointing away from the sun and we're farther away from it, we have a much cooler period, i.e., a glacial period or an ice age. Now, this really gave scientists a good prediction for what we should see in the dude, I hate this word, by the way, paleoclimatological record. Okay, so paleoclimatology is the study of the climate of Earth's history. And scientists can approach this from a couple different angles. The first angle is the atmospheric composition, and the second part is the temperatures during those time periods. Now, while Milankovitch gave us a really good theory for what we should see, we really want the data so that we can look back at what was actually happening. And once you take theory and data and you compare it together, you can verify that that theory is real or not real. So at this point, Milankovich's ideas were good ideas, but they weren't actually verified by data. So scientists did this in kind of a clever way. So the first piece of that, which is the atmospheric composition, what they did is a whole bunch of scientists in 1998, they went to a place called Lake Vostok. Now, Lake Vostok is in the Antarctica. And the nice thing about the Antarctica is it stays frozen pretty much all year round. And if you take an ice core sample from the Antarctic ice sheet, you can see all the different seasons, all the different layers for each season across a very long history. And so what scientists did is they drilled into the ice above this lake 2.2 miles down, and they got essentially a 420,000-year-old record for what the atmosphere was like at different time periods in Earth's history. Now, this is awesome. And the thing about ice is that it actually captures air bubbles, and these air bubbles, you can then do an isotopic composition on it and figure out exactly what was in the air at the time. Now, it's a little hard to figure out the H2O levels because H2O is stuck in a bubble of H2O, water in a bubble inside of an ice bubble. So the water composition is a little hard, but it definitely gives you a very clear composition of the greenhouse gases that occurred at any point in Earth's history, at least in this 420,000-year cycle. So that was part one. The second thing they did was to figure out a lot of the temperatures is a bunch of scientists decided to go take sediment samples from the ocean floor. Now, the interesting thing about an ocean floor, and you think about it just like a river or a lake, you can see the different layers of the strata when you go to the Grand Canyon National Park and you see all the different layers, is because underneath the ocean, sea life dies over time and it leaves layers behind. Okay, so what you end up is multiple layers every single year of all the sea life that lived and died during those time periods in Earth's history. And because you can watch you know how our tectonic plates move, so you know which pieces of the crust have been on the surface the longest, you can really identify a spot that's been underwater for a long period of time, and it hasn't actually gone under the Earth's crust into the mantle. It's just been on Earth's surface for a very long period of time, which gives you a very accurate record. And so what they did is they took a very deep core sample of this ocean sediment, and what it gave them back is a full composition of all the ocean floor sea life during the history of Earth. Now, that's cool for two reasons. Number one, it allows you to, first of all, you have to understand that this sea life was highly dependent on ocean temperature as well as the salinity of the water. So it gave you a really good idea of what the temperature was at the time period that each of these different ocean seafloor life lived at, as well as how salty the water was at that time period. So now you take these ice samples where you have the atmospheric composition at that time period, and then you take the ocean sediment floors where you actually know what the temperatures were, and vaboom, you got a beautiful historical record of what the Earth looks like. Now, the interesting thing about the oceanic core samples or floor samples is that it actually gives you 65 million years of Earth's history. Now, that's a long period of time and a lot of really cool data. So they took both of these pieces of data, and what did they do? Well, correlated and corroborated the data into some of these graphs here. I have a full history of the temperature of planet Earth. So, this is where things get a little bit interesting, is now that you have both of these pieces of data, you can then just, you can start actually verifying the theory from the actual data that you have. Now, it took thousands of scientists across the globe many, many years to correlate and corroborate all the data. But once they did that, they had a very nice timeline of the entire Earth's history, up to 65 million years, of what the greenhouse gases look like, as well as what the temperature was during those time periods in Earth's history. Now, it turns out that when they compared the data to Milankovitch, Milankovitch was right. We went through these warming and cooling cycles. So we started going through these cycles at about 41,000 year periods. And it was very easy to see during the Pliocene era that every 40,000 years you would end up in an ice age or a warm period. Now, what was strange is about 900,000 years ago, they started seeing a slight deviation from this. And instead of a 40,000 year cycle, they started seeing a 100,000 year cycle. Now, this was weird at first, but scientists kind of thought about it, and they have some ideas. And the more pressing idea, or the most popular idea so far, is that because Earth's temperature had gotten so cold that it takes the combination, the additive effect of both the obliquity as well as the eccentricity, so the shape of Earth's orbit, so you have to be closer in an actual circle, as well as pointed towards the sun more at this specific time period to get us out of ice ages. Now, that's interesting to think about, right? So you have to be closer to the sun and more pointed to it. Otherwise, Earth would be stuck in a perpetual ice age. Yay. So what does that mean? Well, it means that we're lucky. It means that we're not in an ice age. And how long until the next ice age? Well, this was a question that a lot of people wondered about back in the 1960s. And it turns out, based on these cycles and based on pairing up the data, it looks like we could potentially go into another ice age over the next 10 to 12,000 years. Now, Milankovitch had another larger time box, which was a 400,000 year cycle. And this 400,000 year cycle means once every 400,000 years, you'd end up with a slightly longer warm period, because based on where the orbits of the planets were, Earth would stay in a much more circular orbit for a much longer period of time. So how does this affect us now? Well, it turns out that we are in this 400,000 year cycle, which means we're going to stay warmer for a much longer period of time. So we're going to stay in this interglacial time period for longer, which means our atmosphere is going to continue to get warmer. Well, it seems pretty basic, right? Well, a lot of people kind of end here, and they're like, well, we're in a warming period, and that explains why the temperature is going up, but it doesn't actually explain why the temperature is going up, and I'll tell you why. So you look at the most recent couple of hundred years, and you look at the temperature data, and our temperature data starts spiking. Now, what started really concerning scientists is, based on the cues that they took from the Milankovitch cycle, they figured that Earth's temperature should mostly follow the solar radiation levels that we see. So when you have a lot of extra solar radiation, the temperature should go up. When you have a lot less solar radiation, the temperature should go down. Now, for the most part, this actually tracked pretty well. And so if you see here, I got a nice little plot, and this is coming from the Stanford Solar Research Center. So up until about 1960, the temperature data really mapped almost exact to the solar radiation data. Now, you see a deviation once you hit the 1960s, and all of a sudden, the temperature starts rising pretty quickly. Now, this is a little weird, and the scientists were trying to figure out why, and so then they decided to go try to figure out what was causing this deviation from the solar radiation. And so what they did is they took a whole bunch of different data from across the board. Now, this included the sulfite in the air, volcanic activity, ozone, in terms of how much radiation was being blocked or absorbed or reflected, our albedo. Our albedo is how much energy is reflected from the clouds or the ice on the planet, to see if that had the effect. And then they mapped greenhouse gases. Now, out of all these things, the thing that seemed to track the best towards actually explaining why the temperature was deviating ended up being greenhouse gases. Now, this is a very tricky thing, right? Because all of a sudden you have a situation where you have correlating data and some kind of a causal effect. Now, it's repeated many, many times in science that correlation does not mean causation, which is true. That can be proven in a lot of different cases. So there's a funny thing right now going on about 5G causes more people to get COVID-19, or 5G affects people to get sick, or all these things. The problem is the 5G map is a population density map. And if you look at population density where 5G is up high, well, you could probably correlate to the number of people that eat Taco Bell is directly related to the number of people that are using 5G, because the more Taco Bells exist in higher dense population areas, and the 5G maps to a population area. So correlation does not mean causation. So by the way, if you didn't get that, I'm making fun of the whole 5G conspiracy thing, right? They're just showing population maps and saying that things map. Well, they don't. They're just population maps. And the denser the population, the more Taco Bell, the more 5G, the more of pretty much everything. So in this case, you got to be really careful to make sure that you're not making the classic mistake of correlation means causation. And so scientists, I think, in this particular case did a really, really good job, because as this graph kind of shows, they really looked at all the things that were potentially attributing to climate change, and the only thing that actually explained the effect, the only things that went in the same direction out of everything that they checked over, by the way, multiple decades. This didn't just happen in like a couple scientists in a couple years. It happened thousands of scientists over many, many decades. The only thing that actually made sense was greenhouse gases going up and the temperature going up. So there was a direct correlation. Now, if you look at the data, and they mapped back to the Solar Research Center data, they put the CO2 directly on top of the solar data, and you see that the solar radiance tracks pretty good with the temperature, and then as the CO2 spikes up, all of a sudden it starts deviating from the solar data, right? Well, what does this mean? As far as they can tell, it means that the CO2 levels going up is what's causing the deviation from the solar radiation. Now, CO2 is kind of an interesting thing, and scientists understand a lot of different aspects of it. So first of all, when temperatures go up, when you get out of a glacial cycle, you see that CO2 levels go up. Well, why? Well, because when you're out of a glacial cycle, you have a lot more biodensity, animals and everything else. You have a lot more living things all across the planet. So you see a lot higher levels of CO2 because, it just gets warmer and the rest of the planet is kind of responding. But in this particular case, it's not CO2 responding to the temperature. It's the temperature responding to CO2. And they can show that just because of the deviation from the solar data, if that makes sense. Now, the interesting thing is how does CO2 affect our overall temperature over the history of the Earth? And when you look at a much larger time scale, the CO2 data is kind of all over the map compared to the average global temperatures. Well, what does that mean? That means that CO2 doesn't always directly affect the temperature. And in fact, there's plenty of cases where the CO2 levels are like 400,000 or 4,000 parts per million, and the average global temperature is pretty much constant. Okay, so it means that not at all points in time does CO2 or greenhouse gases in general have a direct effect on the temperature. So why does it have one now? Well, it has one now because you're kind of in the right temperature zone, the right CO2 level zone for CO2 to have the greatest impact on the actual temperature. And so this is where anthropogenic climate change comes in. So anthropogenic climate change is pretty much just means that humans impact on the climate. And while a lot of people argue that humans don't impact the climate, this data says otherwise. Because we understand now that greenhouse gases are causing the deviation from the actual solar radiation temperature, okay, so greenhouse gases we need to go look at. And so that's exactly what scientists did, is they went and they looked at greenhouse gases across the board. They looked at what the biomass or the biomass in the oceans were generating for CO2. They calculated across all the volcanic activity as well as all the deep sea vents. And you can put sensors and actually track this stuff, right? So it's not like, hey, I'm estimating. It's let's put sensors in all these different locations. Let's record the data. Let's record it over many, many years to kind of, or over the entire, 365 days a year, multiple years in a row to really understand how all this stuff affects each other. And so what they found is most of the CO2 that's generated by planet Earth is pretty carbon neutral. It's pretty even across the board, right? So the amount of CO2 that the oceans release and the amount of CO2 that the animal life releases, most of that just gets absorbed by the plant life. But then why are we seeing on a global level the global CO2 levels continuing to rise, or greenhouse gases continuing to rise? Well, then they started tracking all the human-made CO2, and they started tracking trillions of tons of greenhouse gases that were coming from the human population. You put those two maps together, and you're like, oh, that's why the greenhouse gases are spiking so hard. So here's another graph for you. And you can really see that right around that 1950, 1960 time period, spikes in carbon emissions, greenhouse gas emissions across essentially all of the industrialized worlds just started going up drastically. So we're seeing that all the other things that affect the climate don't seem to be affecting the temperature at all. The one thing that does seem to be affecting the temperature, which is the greenhouse gases, is mostly neutral except for the additive effect of what humans are dumping into the atmosphere. Therefore, you can put all the pieces together along with the solar data and say, oh, greenhouse gases are causing this, and humans are putting out excessive greenhouse gases. Therefore, you can kind of go to the conclusion I'm going at, which is therefore humans are impacting the global temperature. Boom. The entire thing chained together with science, dozens or decades of time, tens of thousands of engineers, of scientists verifying all of the data. Okay. Humans, anthropogenic climate change is a reality. Now, this is where scientists start to diverge. And it's important to understand that there is a divergence in the scientific communities, okay? While pretty much all scientists acknowledge that there is climate change, and most scientists agree that humans impact the climate, we realize that, there's a lot of different moving pieces, and climate isn't simple. It's very, very complex, right? There's the glaciation cycles, there's the greenhouse gases, there's the sulfate and our ozone. All these things change the temperature on the planet. And then the question comes into, well, what are the effects of those changes, right? Is too much CO2 a bad thing? Is it a good thing? How high will our temperature get? Because how long will CO2 actually affect the temperature? These are all things that we just don't really know. But I think that understanding that we have a paleoclimatological record now, that we've generated that you can look back and actually see at different time periods in history how the CO2 levels affected temperature. And you can draw some pretty good conclusions based on the animal life as well as the plant life that existed at those time periods, what that could do to our planet going forward. Now, the biggest concerns on this whole thing is really just how fast we're changing the temperature, but we'll get into that in the next episodes. In closing, so today, what did we cover? Well, we covered how our planet's orbit around the sun and the shifting of its axis caused the past ice ages on our planet. We also looked at the data from the glacial ice cores and the deep sea sediment cores to build the entire history of what our paleoclimatological history looks like. And then we also looked at how scientists use the understanding of the Milankovitch cycles as well as that historical data to look at the current data and then do a complete analysis around all the things that are attributing potentially to climate change, narrowing in on the fact that it was greenhouse gases, and then identifying that the largest increase in global averages are coming from humans. Therefore, logically speaking, you can derive that humans are causing climate change, at least at this period in Earth's history. Now, that doesn't mean that the climate isn't always changing. Of course it is. The question is how fast it's changing and what are the current impacts and can we actually affect those impacts? So that was this week's episode. Next episode, we'll cover understanding greenhouse gases specifically, as well as their effects on our planet. We'll cover biomass in terms of the plant life on the planet, as well as ocean acidification and what that causes, pros and cons, along with some of the doomsday scenarios of too little and too much CO2 in our atmosphere. So I hope you enjoyed today's episode. I hope you learned something. If you think I got something wrong, please point it out to me. I'll hopefully make corrections in my next video. And thank you for joining me for Perspectives. Until next time, have a good one.